important role in the transport of persistent organic pollutants. Once released in the source regions, these pollutants can get transported via long-range atmospheric transport and gets deposited in pristine and colder regions. Let us try to understand the fate of one category of such microorganic pollutants, which are known as the POPs, the persistent organic pollutants. Persistence, bioaccumulation, toxicity, and long-range environmental transport are the four characteristic parameters that distinguish POPs from a multitude of other organic chemicals. Some of their physical and chemical properties that determine their fate in the environment are their low water solubility, high lipid solubility, high molecular mass, and low volatility. Atmosphere acts as the primary long-range mechanism for the transport of pollutants. Some of the persistent organic pollutants, including DDT, move from the point of application through the atmosphere and translocate from relatively warm regions to get condensed at colder, higher latitudes. And this phenomenon is dubbed global distillation effect. It explains the deposition of these organic pollutants at high concentrations in the Arctic and glaciated mountain ranges free from the use of such compounds. These contaminants either attenuate naturally into less toxic or non-toxic forms, or they persist in the freshwater ecosystem for a long time, then enter the food chain through bioaccumulation. They are biomagnified to cause a cascading effect on the terrestrial and aquatic biodiversity. Water can get contaminated through leakage of stockpiles, industrial effluents, and agricultural and soil runoffs, and wet or dry deposition. The POPs in surface water are key in defining critical exposure pathways for humans due to water use for drinking and food production. Organic pollutants can travel far distances and accumulate in organisms after entering through the food chains. However, highly lipophilic properties of most of the POPs make them almost insoluble in water. Despite this, the rivers in other surface water bodies provide a perfect integrative medium to monitor the transport and redistribution of POPs. POPs are less soluble in water and more in lipid or fat. Hence, POPs tend to accumulate in living organisms' fatty tissues. The process of bioaccumulation describes the net enrichment of contaminants relative to that in the environment. Bioaccumulation increases the concentration of a contaminant in an organism, generally in food stocks, several folds higher than that in the surrounding environment. Bioaccumulation is the net result of all uptake and loss processes, such as respiratory and dietary uptake, and loss by addition, passive diffusion, metabolism, transfer to offsprings, and growth. Even if taken up by an organism, it does not automatically result in bioaccumulation of the contaminant. An organism can modify the absorbed mixture of contaminants. Some chemicals are retained, whereas others that are more water soluble or degradable are eliminated from the body, resulting in no net accumulation. In the food web, animals thereby show very different bioaccumulation characteristics for various chemicals, both in levels and in their relative composition. Bioaccumulation of toxic POPs into fatty tissues of living organisms can potentially adversely impact human health as well as the environment. Percolation of rainwater through the soil profile is considered unlikely to remove large quantities of POPs from the surface soils, although the surface soils may be transported, that is, by surface runoff or wet and dry deposition, and gets deposited in lakes and riverbed sediments. The resuspension and circulation process in the aquatic environment forms a continuous pollution source worldwide. Legacy POPs such as HCHs, DDT and PCBs are still frequently detectable in the environment, although they have been banned or restricted for decades. Concentration of PBDEs, PFOS and PHs in the environment are increased with social and economic development. Therefore, the residues of POPs might ultimately pass into people through consumption of agricultural food, fish and drinking water. Several factors such as solubility of POPs in water, environment and climate, including soil quality or rainfall, The distance of the pollution sources from the area of application may influence the spread of POPs contamination. It is also understood that the hydrological characteristics of the river basins, such as seasonal variation of flow and activities related to the construction of dams, can also influence the spatial and temporal distribution of POPs in riverine catchments and in surface water as well as in sediment. Let us now discuss the biological and environmental consequences. The Stockholm Convention identified some POPs potential for the damaging environment and human health. Among the 12 toxic substances listed here for being phased out as per the Stockholm Convention, 9 are pesticides. The most common pesticides among the freshwater organic contaminants are DDT, dieldrin, eldrin, chlordin, endrin, Mirex, toxafen and heptachlor. All these pesticides have a long half-life, can break down to intermediate species and cause detrimental health effects. Changes in environmental conditions such as the increase of average temperature or the UVB radiation influence the fate and behavior of POPs and its exposure to humans. Global climate change can influence the fate, transport, and distribution pathways of semi-volatile organic pollutants, including polycyclic aromatic hydrocarbons and POPs, by enhancing the volatilization from the primary and secondary sources and influencing the partitioning between soil, sediment, water, and atmosphere. These processes also include air surface exchange and wet and dry deposition processes. Frequent storm surges may enhance the mobilization of chemicals stored in the soil compartment, which can be transported by land runoffs, making them available to the aquatic organisms. Abiotic degradation is the mechanical degradation of plastics through weather and climate changes. Among the organic contaminants, PCBs, DDT, DDE, DDD, naphthalene, benzopyrene, dioxins, etc. are reported as suspected carcinogens for humans. DDT causes sperm decline, eggshell thinning in birds, and birth defects in many animals, which have been linked to the near elimination of some species of animals. You might be interested to know the level of threat due to the presence of POPs in freshwater resources and the environment. Rapidly developing agricultural and industrial sectors have been accompanied by the widespread application of organochlorine pesticides, making India one of the major producer and consumer of this organochlorine pesticides. Unfortunately, information on organic pollutants in environmental matrices such as air, water and soil is inadequate from India, and there are significant gaps regarding the pathway studies. In India, the concentration of chlorinated pesticides has been detected in almost all the segments of the environment due to their extensive use in the past, which have shown potential to biomagnify or accumulate in animal tissue, human blood, adipose tissue, and breast milk. The Stockholm Convention on POPs, ratified by India in 2006, imposes an obligation to eliminate and restrict the production and use of POPs. Overall, the literature survey suggests that available data on levels of POPs in Indian river waters are limited. However, current studies on rivers and groundwater suggest that compounds such as HCH, DDT and its metabolites are predominant chemical contaminants found along the Indian coast and in several major rivers of India. Data reveals that many regions of India are hotspots of POPs exposure. Beyond the presence of active primary sources, the Indian environment may be sensitive to influence the release from environmental repositories. Compared to the snow-fed rivers of North India, low concentrations of pesticides were detected in the rain-fed rivers of Karnataka, Tamil Nadu and Andhra Pradesh in South India. Once the presence of organic pollutants in freshwater resources is detected, it is required that they be removed from potable water. Efficient techniques for the removal of highly toxic organic compounds from water have drawn significant interest. Application of conventional water purification or treatment methods is limited due to the associated high capital and operational costs and incomplete elimination of POPs, and generation of secondary toxic pollutants. With the advantages of comparatively low cost, simple design and facile operation, adsorption produces no harmful or secondary products and is considered as a promising technology for water decontamination. Conventional adsorbents used are activated carbon, zeolites and other micro or mesoporous materials. The efficiency of adsorption is mainly determined by the adsorption capacity, selectivity, kinetics, and regeneration of the adsorbents. In terms of characteristics of adsorbents, porosity, pore geometry, and specific adsorption sites play vital roles in the effective removal of POPs in water. In addition, the active species such as various functional groups can be encapsulated into the porous materials to enhance the adsorptive selectivity of POPs in water. Let us now summarize this lecture. Widespread anthropogenic sources, complex transport mechanisms, and resistant to degradation make organic compounds a common pollutant in drinking water and food in many instances. Owing to the persistent nature and the long half-life, it is difficult to remove such organic contaminants from wastewater and polluted water. Bioaccumulation and the resistance to removal from the environment make organic pollutants a threat to humanity in the 21st century. And the need to remove organic contaminants put tremendous pressure on the water treatment facilities. Participants, I hope I could give an overview on different aspects of organic pollutants, precisely microorganic pollutants in water and other environmental matrices. Hope you enjoyed the talk. Thank you.